All right, today we're going to be looking at section 5.1. This is approximating area under curves. It kind of begins with a little introduction, and in this little illustration, it shows us kind of like a relationship between the original function f of x. We take a derivative. The derivative tells you the slope of the tangent line, but what does the integral tell you? So it just kind of leads us into this. You have a little application here. It talks about the area under the curve. So the integral is giving us the area under the curve. I think we went 2 pages. Hold on, let me make sure. Yeah. Okay, so here's a little illustration. It talks about a car traveling 60 miles per hour along a straight highway. Velocity is 60. Over 2 hours, we can tell you that they have gone 120 miles. So here's a visual. You have a straight line over 2 hours. This area under the curve makes a rectangle. We can find the area of the rectangle by doing base times height, length times width. And so you have 2 times 60, which they're showing you here, which gives us 120. So sometimes we want to find the area under the curve. Now, not all the time will we have a straight curve. So this is also showing you that when we have a curved line, we might make subintervals. And so it's going to start explaining this process. So you see this line is not a straight line, it's curved. And there's no formula for that. So we'll make rectangles. They're starting in the middle. We can see part of the line is above the black line and part of that red line is below. And same thing here. And this is when it's increasing. It might behave different when you have a decreasing function. But it just says the more rectangles we make, the closer we can get to the area. There's less error. The white space is shrinking as I make more and more rectangles. And then here they make 64 of them, okay, really, really small. It almost like it gets pretty close or pretty perfect. So we're trying to estimate the area under the curve of a graph between the graph and the x-axis. So notice it stops at the x-axis. It does not go below. It explains a little bit of this. Again, we're going to be approximating the area using Riemann sums. And this is just describing that process. Okay. So first we're going to make a regular partition. So we have a starting point, which they're calling A, and an end point, which we call B. We take the difference, so we get the range, and divide that by how many subdivisions or sections we want. So the change in X is what we call the partition that we're going to be our width of our rectangles, basically on the X-axis. And then again, this just kind of goes over the mathematical terminology definition. We have the endpoints, subintervals, call them grid points or regular partitions, in case you see some of that vocabulary term. And then we start talking about the actual formulation. So base times height, okay? The height is the y value. That's going to come from whatever the function is, and we're going to plug in whatever that endpoint is. It could be the left point, right point, or the midpoint. And then we're going to multiply that height times the base, or the change in x, the regular partition that we've created up above. And you get some image like this. So this appears to be using the right endpoint. So it's coming to the right, making a rectangle. Coming to the right, making a rectangle. These don't appear to actually be midpoints, but I think they're showing you where it touches the line. So this is not the actual midpoint, left end, or right end. It's just kind of drawing it where it touches. But we can't do that every time, so we just do a regular partition. So here, the Riemann sum is giving you the full definition. We have each height times the base, and add them all up to get the area under the curve. This is called a Riemann sum. You have a left Riemann sum that's going to be using the left endpoint, so that would be always using the smaller value. So between 0 and x1, you will use x0. Between x1 and x2, you use x1, and so forth and so on for the left. For the right Riemann sum, you will use the right endpoint. So again, if I'm using 0 and 1, I would use 1 this time. 1 and 2, I would use 2 this time. Those 2 points make the rectangle. And then you also have the midpoint, which is going to be the middle of those two sections. So between x0 and x1, I would find halfway and use the midpoint. Here are some examples showing you left, right, and midpoint Riemann sums with the same curve. Now you can notice as we say left endpoint, that means we go up until the y value touches that graph, and we just go straight across, whether it goes above or stays below, and then we come down to the next value, the x value, that partition, whatever that distance is. And we do that every time. This line comes up here, goes across, comes down. This line comes up here, goes across, come down. We always start from the left and draw the rectangle going to the right. This one is doing the opposite. It's the right Riemann sum. It's going to start on the right side where it touches the graph, draws the line to the left, and then connects the rectangle. The right height should be touching the graph. Okay. And depending on the function, if it is decreasing, the left endpoint will overestimate. If it is increasing, the left endpoint will underestimate, and vice versa. The midpoint gives you like the middle. So it just goes to the midpoint where it touches and extends left and right to the endpoint. Here are some functions and some examples showing you how they use a function, use the Riemann sums and the rectangles to find the heights. And here's what I'm saying. Here's an increasing function. And when they use the left endpoint, since the graph is continually going up, this left endpoint is going to underestimate the area. I believe they do this function with the right endpoint. Okay, so here it is with the right Riemann sum, same increasing function. Right Riemann sum is going to overestimate. All of these rectangles are going above. And here's a midpoint where you have a little bit above and a little bit below. So the midpoint gives you about an average. Pretty close. And then each page is showing you the calculations, height times the change in x. This is now going over sigma notation, so we can represent the Riemann sum with a summation. Okay, summation is a Greek symbol sigma. Here are some properties. Some, when you add up from 1 to 99 or 1 to some number, a little formula that kind of helps you add those numbers up, whether it be something squared or some other formula. I have a few here. Some rules, you have a constant multiple. When you're doing a summation, you can just factor out that multiple, add up all those values and multiply at the end. Have addition rule, adding two terms, you can just do each summation individually. Here are some sums of powers. If it's just an integer, it's just n times that number. Squaring it, here's a formula. 1 through n, here's a formula. And if you're doing k cubed. And then we have some more useful formulas, which we'll use the calculator and show you how to do some of these with adding Riemann sums, because finding the heights aren't always easily done by hand. So technology will assist us. But this is expressing a Riemann sum as a summation using sigma notation. And then you have it with right, midpoint, and left endpoints. This is what we would use for our function notation. Again, just some more examples, and they're showing you evaluate it with a calculator. They actually use it to plug in starting point, end point from a previous problem that they were just showing us. Some of them you can also look and see them from a calculator. Output. And I think that'll be all the information. So with that, we're going to jump into my math lab and start working some problems.